wait a little bit before we get started, so people have a chance to join. Okay, I guess we could get started. I think we have a good crowd. So welcome back again, everyone, for the last presentation of the day. And the last presentation will be given by Matthew Jacobs from the University of California, Los Angeles. And he's going to tell us about a fast approach to optimal transport.
Great. Thank you for the introduction. So what I'm going to talk about today is a fast algorithm to solve optimal transport problems, and in particular to compute optimal transport maps efficiently. So most of what I'm going to talk about today will actually be in the sort of lower dimensional regular setting. But as I go through it, I'll try to point out where the lower dimensional settings are sort of really being heavily used. And then at the end, I'll try to talk about ways that this could be extended to higher dimensional problems. And I should mention that this is joint work with my former colleague, Flavien Legendre, who is now at ENS Paris. Okay, so I think we sort of all know that solving optimal transport problems is hard. And essentially, right, this is just coming down to the fact that you have this very nonlinear, very non-convex constraint set where you say, okay, I actually have to push one measure to another. And there are lots of, techniques to sort of linearize and convexify this constraint, but a lot of these ideas require you to substantially enlarge the size of your problem. So if you try to apply linear programming, then you're essentially squaring the number of variables. If you do something like Benhamou-Brenier, you're adding an extra time dimension, right? So again, you're enlarging the size of your problem, and computation can quickly become intractable if you want to solve some very large optimal transport problem. And sort of the goal of what we wanted to do with this method was to come up with a way to sort of efficiently and accurately solve optimal transport problems without substantially enlarging the amount of memory that you need to store, and also with computation time that's scaling in a reasonable way with your data. So let me just show you guys an example, and I'm going to compare what our algorithm produces to some other, to Benhamou-Brenier, right, which is sort of like the most well-known approach to doing optimal transport, at least in lower dimensions. And this is sort of my favorite example of doing optimal transport. So I have an image of Pikachu, I have an image of Raichu, and I want to find the optimal transport map between them. And what I'm going to display in these computations is the displacement interpolant between them. So you compute the map, you look at all of the pairs of points. So if I send some point x to t of x, And then I'm going to create some video where I watch the particles travel along these paths. And so if you compute this displacement interpolant with Benhamou-Bernier, you get something that looks like this. And so you see that in between, you sort of have this very diffuse density. And that's not what should really happen. Okay, and this is just some inaccuracy that's baked into the method. You get some numerical dissipation that's unavoidable unless you try to go to, absurdly large problem sizes, which are sort of intractable. And so here is the same example using our method. And so what you get is something that is much sharper and more accurate. And what I should point out is this example with Benhamou-Bernier. This is a 512 by 512 pixel image. We solved it using basically the fastest way that we know how to solve Benhamou-Bernier. And it took like 5 minutes to reach this level of accuracy. In this example, we were using a 1024 by 1024 pixel image, and we could compute this interpolant in 20 seconds. So in terms of the computation time and in terms of the size of the problems that are actually tractable, you can do it much, much faster using the back and forth method. So let me try to explain what we did and how you can sort of avoid having to store this huge amount of memory and have faster computation times. So the way that we approach the problem is to look at the convex dual. Right, so this is the Kantorovich dual formula. And okay, initially what you have here is a linear programming problem, but there are ways that you can transform it into something that's nicer, which I'll talk about in the next few slides. Once we have this dual problem, we're going to apply gradient ascent. And there, the key is that you do this gradient ascent in a stable norm. And so when you have this stability guarantee, you know that you are improving the value of the problem in every step. You know that your convergence rate will be independent of your problem size. We're then going to accelerate the convergence of the algorithm by exploiting something that's called C conjugacy, right? Which is this very nice special property that optimal transport problems have. And I'll also explain that in more detail in the next few slides. And the point is, if I have measures that are sampled on a grid with n points, then I only need O(n) memory, and I can also solve the problem in O(n) log n complexity per iteration. So the method is scaling really nicely with the problem size. And I'm going to just focus on this quadratic cost, where you just take the Euclidean distance between 2 points and square it. But you could consider more general costs if you wanted to. So like I said, the starting point is the Kantorovich dual problem, right? So you take your original problem, you relax it by introducing these transport plans, but of course the problem is now you significantly enlarge the size of the problem because you have to square the number of variables. You have to say, for each pair of points, x and y, how much mass do I send between X and Y? Of course, when you go to the dual problem, you don't have n squared variables anymore because you just have your Kantorovich potentials, which are just functions that integrate against the measures. So they should be defined on the same spaces as your measures. And now the sort of n squaredness of linear programming is just instead encoded in the constraint. So you're saying that phi plus psi has to be bounded by this cost. And the key is that you can really eliminate variables when you think about this dual formulation of the problem. And the key is that if I fix either one of my Kantorovich potentials, then the other one is automatically determined, right? So I'm trying to maximize this problem. And what I should do is if I fix one of these potentials, then I can look at this constraint and the largest choice that I can make for the other guy is clear. So if you do this, this is where you get the C transform, which in my opinion is my favorite way to think about optimal transport. So if I have some solution pair, then I know that they need to be related to each other through these C transforms. So if I fix psi, the best thing I can do for phi is to subtract psi to the other side and choose the largest thing that respects the constraint. And vice versa for the other guy, right? And when you do these two things, you get these C transforms. And so what's nice now is if I go back to this problem, I can eliminate my constraints by either replacing one of these two, either phi or psi, by the C transform of the other function. And when I do that, I eliminate all of these constraints and I get some nice unconstrained problem where I can start applying gradient ascent to. I should mention, when I know that phi is equal to psi c, and I know that psi is equal to phi c, these two functions are said to be C conjugate. And this is this C conjugacy property that I was mentioning earlier. That's going to eventually accelerate the convergence. So, like I said, you can fix one of these two functions and eliminate the other by introducing these C transforms. And you have a free choice, right? You can choose to eliminate either phi or psi. So I could define a new dual functional that just uses the phi variable, or I could define a new dual function that's only using this psi variable. And the idea of this method is to actually use both. So rather than try to optimize just one of these functionals, we're going to optimize both of them at the same time. So I'm going to do a gradient ascent step on J. And then what I'm going to do is I'm going to take a C transform, convert my variables into psi space, and then do a gradient ascent step on I. And then I'm just going to keep switching back and forth between doing gradient ascent on these two functionals. And the advantage of working with both of these simultaneously is you're sort of building up different features when you work with each of these two functionals. So you can imagine that certain features are easier to build in one space than the other. And so if you try to do ascent in both spaces, you ultimately get a faster convergence rate. And this idea shows up in other places too. So in some sense, the Sinkhorn algorithm is also doing this idea where you're constantly switching between two different variables. So somehow this is a very natural idea in optimal transport. And right, if you have two equivalent functionals, why break some symmetry that you have by choosing one of them? It's better to work with both. Okay, so we want to do gradient ascent on these problems. And in order to do that, we have to know how to take gradients of the C transform term. That's the part that is maybe not so obvious, how you actually compute those things. And the key is to look at the maps that you get when you ask what is the argmin of these C transforms. So I can define a map T phi, and that just tells me what is the minimizer of the C transform at a point X. And I can do the same thing with T psi. And obviously these maps don't seem very easy to compute because it looks like you have to solve an optimization problem. But the thing that's nice is if you know that your two potentials are C conjugate, then you can compute these maps in terms of one another. So T phi has a very simple formula in terms of psi, and T psi has a very simple formula in terms of phi. And it also turns out that these two maps are actually inverse to one another. Okay, so we see that these maps are computable. And this is important because this is actually how you compute variations of the C transform. So you want to ask, if I perturb my phi by some other function and I take the C transform, how do things change? And it turns out that what you end up with is you get your perturbing function evaluated at this map. And so if I take this first variation of say J, then the linear term is very easy. I should just have U integrated against that measure. And then when I take the variation of the C transform term, I get U, but evaluated at this map. And if I want to remove the map from U, I can just do that by pushing forward the measure. Okay, so ultimately I can write this as the integration of U against this measure nu minus the push forward of this measure mu. And again, we know how to compute this push forward map as long as we have two C conjugate potentials. And therefore, we know how to take gradient ascent steps. And actually, this also points out why solving this dual problem gives you an optimal map that pushes one measure to another. The only way that this first variation can vanish is if T phi is pushing mu to nu. So here's the method. What's going to happen is we are going to do a gradient ascent step on the phi space. We take a C transform and then move into psi space. We do a gradient ascent step there. And then again, we just take a C transform to move back into phi space, and we just keep iterating this. If you look at these gradient ascent formulas, you see that you have this first variation. And in front of it, there's this inverse Laplacian operator. And this is what you need to do to make this algorithm stable. So without this inverse Laplacian, which you can think of as a preconditioner, or you can think about it as doing gradient ascent in the correct norm, you don't really have stability guarantees. So when you put this inverse Laplacian in front of these gradient terms, then your step size sigma, you can take it to be basically independent of your problem size. Otherwise, you would anticipate as you get larger and larger and larger problems, you have some instability and you would be forced to take smaller and smaller sigmas. And what I want to point out is from the structure of this algorithm, whenever I need to compute these variations, I will already know that psi and phi are C conjugate to one another. So in the third line, when I need to compute this map T psi, I already know that T psi is the C transform of phi. And so I have this very simple formula where I can just compute it directly. So without this alternating C transform structure, you might not be able to compute these gradient steps. So the questions you can ask are these gradient ascent steps really stable? Are they really increasing the value of these dual problems? And you could also ask, well, this C transforms, it's nice that you switch between these spaces and you know how to compute the gradients, but are these steps messing up the values? So is it possible when I take the C transform, could I actually decrease the value of my functional? And the answer to that is no. So the C transform has this really nice property that if I take it twice, the value of my function increases. And if I take it 3 times, it's the same thing as just taking it once. So this is actually very, very similar to the behavior of a Legendre transform. And all of these transforms are actually very related to each other. And so you can use these properties to see that if I take a phi, I take its C transform and bring it into the psi space, and I plug it into I, actually the value has to get bigger. That's just going to be because when I do this double C transform, I actually had to increase the value of the function. I'm integrating it against a positive measure, and so the value of the problem has to go up. And now let me just say, where is this inverse Laplacian operator coming from? And this is related to something that I like to call the fundamental lemma of optimization, but I don't think that this is the standard name for this result. But if you have some concave function and you know how to bound its Hessian in some Hilbert space H, then you can guarantee that these gradient ascent steps are going to converge to the maximizer. And you get this explicit convergence rate. And when you look at the convergence rate, you see that you want to choose H to be as weak of a norm as possible. So a weaker norm means that your convergence rate will be faster. So you essentially want to choose the Hilbert space H, where you can guarantee this bound on the Hessian, and then H is as weak as it possibly can be. And so for optimal transport, the natural thing is to choose the H1 metric, or choose H1 as a Hilbert space. So if you look at this second variation, you get this kind of complicated formula, but the point is that you get gradients of this function u that you plug in, as opposed to just the function u itself, which is, perhaps what we're more familiar with in L2 gradient methods. But here you get gradients, and you want to be able to control the L2 norm of this function u squared, the gradient of u. And so the right space to choose here is something like H1. The only issue is you can see here that I'm bounding these other 2 terms that show up in L infinity. And in a lower dimensional problem, that's not such a big deal because you're probably working with some measures that are pretty nice. This looks a little bit more dicey in really high dimensions if, say, your measure mu is something singular that's concentrating on a lower dimensional set. And so one thing that's not entirely clear is if you wanted to start applying this method in high dimensions, is this H1 norm still the right thing to choose? And that is not something that is clear to me yet, but I just want to point out. Okay, so let me actually just go back to the algorithm itself for 1 second. So we now see where all of these steps are coming from. The question is, how do you actually compute them? How do you implement all of these steps? And the one that is the most non-trivial is how do you actually do this C transform? And so it turns out that if you have some structure to your problem, if your data is on a grid, then you can do this C transform extremely quickly. So when you have this squared cost, you can actually explicitly rewrite the C transform in terms of a Legendre transform. You then say, okay, I am doing the Legendre transform on my nice regular grid. And for example, right, in 2 dimensions, you can see that what you need to compute decomposes along all of the dimensions. And what this means is essentially, I just need to compute a bunch of 1D Legendre transforms, right? So I do a Legendre 1D along horizontal lines, then I do it along vertical lines, and then I'm done. And the key is when you're doing that, all you need to do is compute a 1D convex hull. That's easy, and you can do it fast. So if you have n points, you can do this fast Legendre transform in ON operations. If you want to do some kind of a more general cost, the only thing that really matters is, again, that you're on a regular grid and your cost decomposes along dimensions. So if that happens and you have, I should say all of these HIs are convex functions, then there's a divide and conquer way of solving these one-dimensional problems. And the idea is if I have a convex cost and I look at 2 points along a line and I map them, I'm never going to cross the points where they go, right? So if I have 2 points here, they're never going to end up crossed in the target space. And this monotonicity allows you to do a divide and conquer algorithm where you split the even and odd points, you solve it on even and odd points, you come back and interlace the information. And in this case, you can do it in n log n. Okay, so obviously these things are very, very particular to being on a regular nice grid. But at the very end, I'll try to at least suggest something that you can do in higher dimensions. So let me just show you guys a bunch of examples of applying the method to some problems. And what I want to show here are some more difficult computational examples where the optimal map is discontinuous. And in this case, you would expect it to be harder to compute because the regularity theory for these maps is not as nice when they're discontinuous. So here's an example. I start off with a square in the center, and the other measure is going to be 4 smaller squares in the corners. And so the optimal thing to do here is to cut this guy along the cross and send these other things to the corners. And the nice thing about this particular example is it's not that easy, right? We know that this is a case that's hard, but there's an explicit solution, right? So you can write down analytically exactly what this map should be. And so it's a very nice test case. I want you guys to look at this second table here, because this is giving a comparison between how fast you can solve this problem if you do back and forth method, where you do these alternating gradient ascent steps on both problems, versus just doing gradient ascent on only one of the two problems. So you see, if you only do gradient ascent on either I or J, it's way, 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 way slower. So you can see you need way more gradient steps to get the same level of error. And so this idea of working with both problems, I think, is something that's very important in general and should accelerate your method regardless of the setting that you're working in. Okay, so let me just show you guys a few more fun examples. So here are a bunch of disks, and I'm going to map them to another set of disks. And you'll see there's really no way you can anticipate what the solution should look like here. So they sort of cut themselves up in all of these strange different ways. And this is what the optimal thing to do is. This one is actually my personal favorite. We're going to send this jack-o'-lantern face to a Pegasus. And again, right, there's lots of discontinuities, but the method still captures a lot of these fine features extremely well. So if you look around the eyes and the smile at the beginning, you can already see how some of these features form. And so this, at least for these lower dimensional problems, it's very, very difficult to get this level of accuracy using other methods. Oh, okay, this is going to be a, this guy here is Monge, and we are gonna send him to Kantorovich. So this is what that displacement interpolant looks like. Okay, so now that we've done these fun examples, let me just end by just talking about how could you try to extend these ideas into higher dimensions. And so the biggest problem is that these fast C transform algorithms are not applicable. And in fact, even if you're in low dimensions, right, these fast C transform algorithms are not applicable if you're not on a grid. So we very strongly were using the fact that you could decompose the problem along each dimension. So you can't do that. Of course, you always can compute a naive C transform by just checking every single option and looking at the best one. But of course, now you're doing something that has O(n) squared cost. So you're kind of getting back to all of these other methods that are very expensive. So it kind of defeats the purpose. And so the question is, could you do better? Is there some way to do a C transform more efficiently? And of course, the other problem is, can you prove some kind of gradient stability in a higher dimensional space? So this analysis of choosing H1 is no longer so clear. So there is some question of what is the right Hilbert space to choose. And if you choose something that isn't L2, right, you're going to have some kind of preconditioner in front of your gradient. How do you compute that in higher dimensions, right? How do you invert a Laplace operator in higher dimensions? And I think those things are not so obvious. However, I would say I'm more concerned about how you do this C transform, because it's very, very nice to apply rigorous PDE theory when you're in low dimensions. You can really see that the theory matches the applications. When you're in high dimensions, I don't know, just try it, and there's some chance that it just works anyway. But let me point out that at least with the C transform, there is a different way to think about it in these unstructured or high dimensional settings. So if I suppose that my measures are just supported on some discrete sets, X and Y, then, right, I just write the C transform. So if I want to evaluate the C transform at some point Y, then I'm just going to minimize the value of phi over all of the points in X. And I also have to add this cost squared. But you can actually think about this as a nearest neighbor problem. So if I embed all of these points in one higher dimension, and I append X with the value of square root of phi at each point, and I just append the points in Y with the value 0, then if I compute the distance between any 2 points, it's exactly this thing that we're trying to optimize in the C transform formula. And so you can compute these C transforms by doing a nearest neighbor search. And so I think that there's certainly hope to do something better than the naive n-squared approach if you use some kind of a nearest neighbor algorithm or some kind of approximate nearest neighbor algorithm. But I have to say, this is not a subject that I know super well. So this is just some idea. So if somebody is a nearest neighbor search expert, I don't know, please try this and report back. So this is sort of last thing I wanted to say. So let me just leave you guys with one last fun video. And thank you for your attention.
Thank you. Very good presentation. Are there questions from the audience?
Hi, I have a question. Can you hear me?
Yeah.
Okay. Actually, I have 2 questions. First is when you're showing the displacement interpolation between Monge and Kantorovich, what's the resolution? How many points, data points are you taking in the picture?
I think that was 1024. I think all of those examples were 1024 by 1024.
Nice. Yeah, it's million points, more than million points.
Yeah.
That's good. Yeah. I do have another question regarding the algorithm. So you're using like C transform, right? So you compute exactly the C conjugate of each back and forth. So I wonder if you replace it by soft C transform, and continue to do your same back and forth algorithm, probably with, I'm not sure, the same norm, but will you get similar algorithm to, say, for example, syncon or something like that?
That's possible. So what do you mean by soft C transform?
Yeah. So I was saying like, so if we go back to the simplest C transform, which is the Legendre transform, right? So you're taking a supremum of something. So instead of taking supremum, you replace it by like line of exponentials.
Oh yeah, okay. Yeah, so I think in that case it is you get something that's very close to Sinkhorn.
I see.
Yeah.
Thank you very much.
Any other questions?
I have a couple. Although this was a nice talk, and this last question was actually quite interesting and intriguing. Right, and because you still, even with the softmax, you still get a map, right? Which is not kind of in the nature of Sinkhorn, but it's interesting to, right? It may solve some of the issues in trying to do this in high dimensions as well. But just to go back to one kind of prior point that you made when you analyzed the Hessian, right? And you said, okay, I need these L infinity estimates, and that kind of gives me stability. So, and you said, if I look at the measures that are very concentrated, right, then I may have difficulty. I mean, I'm actually completely impressed how this method is so robust with when you have zero density, where many other methods would round off a little bit and have some regions of kind of intermediate density, right? But here, this is really impressive. But what happens if you try to do, let's say, in 2D and you put data on the ring and you map it to a square or ball?
You mean like you have some density
On a
that's
circle,
very
yeah. Data
yeah. It does slow down. It absolutely slows down. So it doesn't slow down quite as badly as this formula would suggest. But you can see when you have something that's pretty concentrated, it is slower.
Right. And I was just, because in that case, let's say if you tried, just the direct gradient ascent, right, then one direction would be fine, right? The other direction would be a disaster because you don't have resolution, right? So now when you rock back and forth, does this kind of actually kind of work against you because you don't have enough resolution in one direction?
I think definitely. So so what I would say is, in general, I think you're better off going back and forth.
Sure, right.
But examples like that, yeah, you should definitely go in the direction where you have better regularity.
Right. Yeah, thanks.
Yeah, it's good seeing you, by the way.
Likewise.
So may I pick up, I guess, a related question? Of course, the inverse Laplacian being constant coefficient is convenient to solve.
Yeah.
But I guess this question of concentrated data, you could imagine improving the situation by using an elliptic operator that's well suited to the situation, except for then it becomes hard to solve.
Right. Yeah, absolutely. And so at least for like these lower dimensional examples, it converges so quickly that it doesn't seem worth it to solve like a harder elliptic problem to get better stability. But I think maybe in high dimensions, that would be really important.
Yeah, and remember, I mean, so if you're on a regular grid, you can do Laplace type problems by even fast Fourier transform. But there's all kinds of fast ways of solving elliptic problems.
Yeah.
Okay. Any other questions? I have one question. Those nice sort of transition pictures that you have, for example, changing from Monge to Kantorovich, because you're moving mass. Do you have to normalize the mass so that they have the same total mass before you can do the transformation, right?
Yeah, definitely.
Okay.
So that happened in all of these examples. Yeah, so I don't always know whether, if the thing you really care about is image morphing. I think it's not clear if this interpolant is really giving you the thing that you want, especially because you have to do some of these renormalizations. But that's a separate question.
Right. Thank you. Any other question? Okay, if not, then I guess we can close this session for today, and